Alright, today we're going to get into quite a challenging concept for trig students, and that is understanding the limitation of inverse trig functions. So we know with regular trig functions like sine and cosine, right, their domain is all real numbers, meaning that for any angle that we put, we will get a ratio of sides of a right triangle that corresponds to that angle. And sometimes, of course, two different angles, two different inputs will have the same output. But of course, we can't have it where one input will have more than one output, because that violates the fundamental properties of a function. Y is a function of x. So we see here that we want to deal with functions, because when we deal with functions, our life is a lot easier. For example, right, if we have a function like y equals x squared, if I want to graph that here, this is what it looks like. It's just an upwards parabola. And so, or let me write it as f of x. Right, f of x equals x squared. This is what it looks like. And so if we want to find the inverse function, we essentially switch the x's and the y's and then solve for this new f inverse of x. And if you, here, let me write the square down here. And again, I know what f inverse of x equals to. F inverse of x equals to, in this case, plus or minus the square root of x. And that is a huge problem. Why is that a huge problem? Well, let me plug in an input here. F inverse of, let's say, 1, I get plus or minus 1. And that's more than one output. One input, in this case, is having two outputs. That violates the fundamental properties of a function. Right? For every one input, we should get only one output. So in order to solve this problem, we need to restrict the range. And so let me, for example, draw this function so you kind of see what I'm talking about. So if I draw this function here, it's just a sideways parabola. And so one thing to note here also with inverse functions is that they are a reflection over the line y equals x. So if I kind of draw y equals x here in a kind of dashed line, hopefully you can kind of see, again, I'm not an artist, but you can kind of see here that these are reflections of each other over this line y equals x. And so that is true for every inverse function. F of x and f inverse of x, they are reflections of each other over this line y equals x. And so now to solve this problem, and again, another way to justify that this sideways parabola is not y as a function of x, is if we do the vertical line test. And if we do the vertical line test, we see here that when I draw these vertical lines, that it intersects with the function more than one time. In this case, it intersects with the function, or not with a function, with this relation, perhaps. Well, we think it's a function at first, but now I'm disproving that by saying, hey, it's intersecting with this sideways parabola more than once, and therefore it's not a function. And so how do we solve this issue? Well, in order to solve this issue, we need to actually restrict the range of this function. For example, if I made this only positive root x, then this half would not be there, and so we'd only have like a positive square root function, and this itself would be fine because it would intersect only one time. Or say, hey, I want to make this just the negative square root of x function, then we don't have this upward half, we only have this downward half, and hey, it only intersects once, so we're good. So this is how we solve these problems of, hey, we have found the inverse, and now it's, we see that this plus or minus, that means that it's not a function, y is a function of x, it fails the vertical line test. That means we have to restrict the range of the function in order to make sure that it is y as a function of x. And so this same problem occurs in the world of trigonometry as well. Because if you think that with inverse trig functions, right, like how with regular trig functions, you input any angle, you will get the corresponding ratio of sides of a triangle. But then if you input that ratio that you get, then hey, you're getting all of these different angles, and because it's a reflection over the line y equals x, that means that it won't pass the vertical line test. And you can see this here, like for example, if I go ahead and draw the sine function here, and then I'll draw sine inverse of x, and I'm going to actually draw these in two separate Cartesian planes, or coordinate planes we call them, just because it'll get a little messy, because sine is a periodic function, it goes on forever. So if we draw sine of x here, I'm going to try my best here to draw sine of x. Let's see here, maybe like 1 period. Yeah, this is 1. This is -1 right here, and it kind of looks like this. Kind of, okay. Could have done a better job. And so this is my drawing of f of x equals sine of x. And hopefully you know that f inverse of x is just, we sometimes call it arc sine of x or sine inverse of x. Both are correct, both mean the same thing. And so if we actually draw this here, which is a reflection of this, I'm not going to draw the entire thing, but hopefully you see that because when it reflects over the line y equals x, that we're going to get the exact same problem like we saw with x squared, and that it's going to fail the vertical line test. And so because of that, we have chosen to restrict the domain of sine inverse of x, restrict the range of sine inverse of x, so that we get a function that looks something like this. And so what I mean by that is this is what sine inverse of x looks like. Again, hopefully you kind of see it's very much resemblant of the sine of x function if you look at it kind of sideways, right? Or like you think of the y-axis as the x-axis, and then the x-axis is the y-axis, because then your x's and y switch when you're dealing with inverse functions. And so here, the important thing to notice, actually no, there is no arrow here. This range is actually restricted because there are infinitely many angles that can produce that same ratio sides of a triangle. Because remember, one often thing that people commonly miss is that they forget what you're inputting into these inverse trig functions. For example, here, you are inputting an angle. The output is a ratio. Here, since x's and y switch, they're inverses, you're actually inputting a ratio, and then the output is the angle. And so because of that, the output, when we're talking about range, we mean output. This range is restricted from negative pi halves to pi halves, because if we go outside of negative pi halves to pi halves, like if I extended this all the way from negative pi halves to pi, it'll automatically already not pass that vertical line test. So we as mathematicians have agreed, let's restrict this sine inverse of x or arc sine of x domain, range. So I have to try my best not to mix up those words, okay, because it's important to distinguish between the two. We've agreed as mathematicians to restrict it from negative pi over 2 to pi over 2 because we are still able to get all the information. We are able to get more information based off of the information we get off of this, and that's what I'm going to talk about here. And so, because of this restricted range, if you are asked, for example, sometimes to find the angles, right? If you're given sine of theta equals to some ratio, and you're asked to find all solutions between 0 and 2 pi, again, very standard question, if you just put sine inverse of that ratio into your calculator, chances are that you will only get one of the two solutions, right? I mean, like, again, or like you will not get all the solutions for, sine of that angle, okay? And so what I mean by that is if we do a practice problem here, and I want you to first pause the video and try to do it yourself, so that you can kind of see, like, if you've not learned this before, or you're reviewing your trigonometry, you will probably find yourself just giving an incomplete answer. And so let me erase the board here and show you what I'm talking about. Well, first I want you to solve this problem that I'm about to give you here. And so this problem here is I'm going to ask you to erase more. I'm going to ask you to find. Let me lower this here a little bit. To find all solutions to or of sine of theta equals to negative 0.4216, and then this will be when theta is greater than or equal to 0 and less than 2 pi. Okay, this is a problem I just made up here. Find all the solutions of this for all, find all the theta values here in this interval. So I want you to see here, will you be able to solve this problem? Just, don't look up stuff. Don't use ChatGPT or anything like that. Just try to do this on your own. You can use a calculator, obviously. We're going to need to use a calculator. But see what we can do. Alright, assuming you've attempted to solve this problem here, hopefully you did a sine inverse or an arc sine of both sides, and you found that theta equals arc sine, or sine inverse, of negative 0.4216, and then you got an angle. And again, we're dealing with radians here. Make sure you're in radian mode. This is a good check. If you're in radian mode, you should have gotten negative 0.435 radians. And then so now we have to see here, is this all of our, is this the only solution? Because it's asking for all solutions. Hint, no, you're actually missing a solution here. And that solution is outside of our range of arcsine. Because recall, the range of arcsine is from, right, arcsine, right, if we look, let me draw here, arcsine of x, right, our domain, which hopefully you should know because it's the range of the sine function, is negative 1 to 1, because remember the domain and the range flip. But then here our range, which is of course restricted, right? It's not the domain of the sine function, which is our real numbers. No, I just told you guys that we restricted it to negative pi over 2 to pi over 2. And so if we look at our angle here, what we got is, again, if we look at pi over 2 here, pi over 2 is approximately 1.57, and then negative pi over 2 is just approximately negative 1.57. This is in between negative 1.57 and 1.57, but there could still be an angle that's outside of negative pi over 2 and pi over 2, and an angle that's outside of this that can still give us, of course, sine of, that angle that's outside of this range here that still equals to negative 0.416. And so how do we go about this here? So again, I told you that this makes sense based off of this, but now we have to look at this here. Let's graph kind of this angle here in radians, and again we can kind of graph this and make approximations. I'm going to draw kind of like a unit circle-ish diagram, and so remember this is 0 or 6.28, okay, and then this is 3.14, right? This is pi, 2 pi, or 0. And again, we're dealing with radians here. This is 1.57, also known as pi over 2, and then this is negative negative 1.57, or negative pi halves over here. And so this is something, again, hopefully this makes sense. And so now, if we think about this, where negative 0.435 is, if we think about negative, first of all, that means that we're not, again, we can always add 2 pi to this, but let's first talk about, again, what I mean by 2 pi is we can add, it's going to be here, first of all. If we do this, it's not going to be in the standard position. What I mean by standard position is that we start here. This is the initial side, is the positive side of, our x-axis, and then we go counterclockwise. We would actually go from the initial side, and we'd actually go clockwise, okay? So what I mean by that is this negative right here, this angle, right? We're starting here. This is actually going to be our negative 0.435. It's going to be right here. this is where it'll be. But again, if you're not comfortable with this negative here, you can always just add 2 pi or add 6.28. So then you can get the coterminal angle, and you'll come back here. Okay, so for the sake of just understanding, I'm going to keep it in the negative here. And so I've done this, just move down here, again moving clockwise and not counterclockwise because we're not in standard position. We're not doing stuff in standard position because of this negative sign, so we're down here. And so now we need to think about, okay, this is a negative value, right? This ratio is negative. And when we think about where is sign negative, we know that all, again, have you heard of it? Maybe you've heard of this, ASTC, this acronym. All students take calculus. Maybe you've heard of this. This just means in quadrant 1, all the trig, all sine, cosine, tangent are positive, right? Those ratios are the outputs of sine, cosine, tangent are positive. Here, only the outputs of sine are positive, and then the outputs of cosine, tangent, of course, you can, the reciprocals as well, like secant, cosecant, and cotangent, they will all be negative here, so only sine will be positive here. And by only that, you can assume, of course, the rest will be negative. So then here, only tangent is positive, and then here, only cosine is positive. And so here, we see here that sine is negative here, which makes sense because only cosine is positive here. But where else is sine negative? Well, sine is negative here as well. Sine is negative here as well in the third quadrant. So how do we get to the third quadrant? Well, we need to first of all think, again, T and C is where, again, this is C, this is where, again, this makes sense, right, that we have a negative ratio because sine is negative in the fourth quadrant, but sine is also negative in the third quadrant. So we have a solution in the third quadrant. And so in order to find this solution here, all we got to first do is we need to let's get the coterminal angle. And the coterminal angle, I told you can do this before, is just add 6.28 to this. And so if we add 6.28 to this, and we get the coterminal angle, this will be then 5.848. Okay, remember this will just be then the same as 5.848 radians. I'm going to add RAD here. Rad. Okay, this is these angles are the same. Okay, and so because now that I added 2 pi to this, so now we're dealing with standard position stuff, right? This is the same as this, right? Just directionally, right? We're just going... We're getting to the same answer in 2 different ways. And so now we just need to think, hey, isn't our angle is going to be somewhere here, right? This is where it's probably going to be, right? This is where that missing solution is going to be. And so in order to think about this here, again, this is 5.848 right here, which is the same as, again, 6.28 minus 0.435. And so really, if we think about how we get from here to here, we need to first get from here to here, which is 6.28, and then find this angle right here, which again is symmetrical. This angle right here, let me draw a better sketch here. This angle right here is symmetrical to this. So this theta right here for this guy is also going to be positive 0.435. In the first quadrant, right, this is negative, but these angles are congruent. These angles are the same because of symmetry. So I can just add 0.435 here. So now, then, because exploiting this concept of symmetry here, in order to get to this missing theta right here, wherever this guy is, I just add another pi, right? And hopefully this makes sense, given if you look at it from this area here, if you just forget this thing, like if you look at this, from here to here is 180 degrees, because this, like, in essence is a horizontal line. So you're going from here to here is 180 degrees. So your missing theta is just, okay, first of all, this is negative. Found the coterminal angle. know that if I just add this, right, 5.848 plus 0.435, I get 6.28, but then hey, let me exploit symmetry since I know that this and this, right, these angles in essence will be the same. So in order to find that, I first go all the way up here, right? I add 0.435 like until I get positive 0.435 here in the first quadrant, and then to get to the third quadrant from here, I just add a pi. And so when I add a pi here, that's going to be my missing theta. My theta in question will be right here, okay? So then, and again, sorry if this is a little messy, you can ask me questions in the comments if you're confused. And so because I'm adding the pi here, it's just really going to be our theta in question, our missing theta missing, is just going to be this 0.435 plus pi, positive 0.435 plus pi. And so then that's going to be then 3.577. And so that's it. This is the theta that most people miss. So all the solutions, right? So our theta will not just be, well, it'll not just be negative 0.435, okay? People will only circle this answer, but that's not correct. We also have this too. Theta will also be 3.577, and so this is our answer. And this is the one that most people miss. And so you can test this out if you're skeptical. Put this into your calculator. If you do sine of 3.577, wait, you will also get negative 0.4216. Isn't that cool? So again, this is talking, again, the whole point of this is to, of course, not only see that there are limitations to the arcsine function because we've restricted it to this range here that you see in your calculator, right? Your calculator strictly goes off on this range, or otherwise it would crash, it would hallucinate if not given this range because of the violations, right, with the fundamental properties of functions. So because of this range here, right, we're only getting this, and then from this we have to exploit symmetry essentially, like hey, this angle right here, this small angle is the same as this small angle right here in the positive, right, and then hey, from here I get to here, which is to pi. So just really exploiting symmetry and saying hey, it's from this I just have to get to this, where it's another instance where of course sine is negative in the third quadrant, and then hey, I have this angle too that I should not ignore. So it's just manipulating, it's essentially using this to get this. And again, most people miss this angle, and so it's important to realize that because of the restriction we have to do some more work by hand in order to actually get this second theta, which also gives this. And it's also, again, this is between 0 and 2 pi. If it didn't have 0 and 2 pi, then there would be infinitely many solutions, and then of course you'd have to generalize it by like an n times something pi related. And so that's, again, this is it. Just make sure, the calculator won't give you the full answer. You got to still do the work by hand and exploit symmetry with respect to angles and kind of how they work. And so again, yeah, that's kind of it.